The next talk is given by Chelsea Edmonds, and this is joint work with Larry Paulson, and it's quite a change of scenery from hybrid systems to Lovász local lemma.
Great. I'll get started 1 minute early and take advantage of the extra time. So good afternoon, everyone. As said, so this is work actually based on the last chapter of my PhD thesis, supported by my supervisor, Larry Paulson, while I was at Cambridge. I'm now at the University of Sheffield, who are supporting me coming today, which is very nice. So today, basically, I want to give you some insight into how we go about doing probabilistic proofs for combinatorial structures in a way which isn't just about hacking away at getting one proof out, but we do it in a smart way that mirrors the kind of techniques you might see on paper. And this very much fits with my kind of philosophy for formalisation, which is focusing on techniques over simply formalising theorems. So what I'm going to do in the next 25 minutes or so is introduce you to what I'm talking about when I say the probabilistic method for combinatorics, and then go over the three main things that this paper contributes. So looking at a general framework for the probabilistic method, the formalisation of the Lovász local lemma, and then looking at a few sample applications to show how it actually works in practice. And I think the really interesting thing about this work, from my perspective as well, came not just from doing the formalisation, but from some of the insights that we saw both from a mathematical and formalisation perspective. So I'm going to spend a little time at the end discussing some of the key insights there. Great, so what is the probabilistic method? It's this basically go-to technique now in a lot of combinatorics work, which allows us to prove the existence of a certain combinatorial structure with a desirable probability, desirable kind of property, sorry. So we'll usually define some kind of randomness or probability space over a structure or a set of structures, and then we show that that probability has to be positive, so strictly non-zero, and obviously if we're working in a finite space, there must be something in the probability space which therefore satisfies that property. And you can also kind of use the complement of that reasoning in reverse. So the go-to textbook on this subject, I think mathematically, would be Allen and Spencer's book. And what I've done up here is summarize a bunch of the different techniques. And what their textbook does is each chapter is dedicated to a different technique in probability, and then they show how they can apply this in a number of different ways to combinatorial problems, which fits in really nicely with what I was trying to do with formalisation more generally. So why we want to do this, there's currently 3 formalizations that I could find using the probabilistic method for combinatorics. They were all in Isabelle. They use these 3 kind of techniques on the right, so linearity of expectation, alterations, and the second moment method, but they were very much focused on formalizing a specific theorem. What this presentation is going to focus on is looking at some of the more kind of basic kind of framework and techniques to reduce the barriers to even starting a probabilistic proof in a formal environment, as well as the Lovász local lemma. That said, a lot of proof assistants, not just Isabelle, have the basics that you need in terms of these probabilistic techniques already formalized, which I do want to recognize. So even we're seeing recent formalization of martingales across a few different proof assistants as well. That said, the Lovász local lemma hasn't been formalized in any system previously. So what does a proof look like? So this is a really basic example of a proof on hypergraphs, so being a generalization of, I guess, graphs where edges can have any size on hypergraph colourings. So it's fairly simple, only 5 lines, as you can see. We very much follow the pattern of introducing randomness, establishing a non-zero probability, or a less than 1, and using the complement to obtain our exemplar structure. So let's start off with the first bit, a general framework. And I look at the few of the kind of problems that this aims to solve. So there are 2 prior pieces of work that I kind of worked on to get myself started in this field. One was actually the formalisation we did for a paper published at CPP last year on the Bailog-Semerady-Gowers theorem that used an alteration kind of like technique. And then there was that really simple lemma I just showed you at the start on hypergraph colourings. So I thought this is a good test case. Let me see how this goes. This is 1 line of that 5-line proof. So it wasn't as easy as it looked, let's just say that. And it was a really kind of good, this was very much an initial hack to see, well, what are the challenges? What are the barriers that I'm immediately facing when I do these kind of proofs? And a lot of the challenges were similar, but also you could see some clear kind of probabilistic aspects to them. So there was a reliance on human intuition, but it was quite a different kind of intuition than what I was used to in other, say, combinatorial counting problems, which I formalized before. A lot of complex calculations, that's fairly standard for anyone who's done mathematical formalizations. And then the interesting one, particularly for probability, was the setup involved. There was a huge amount of kind of setup that you needed to do at the start of each proof in a formal environment, which on paper you wouldn't even consider doing. So there's definitely some potential for generalization here. So how Allen and Spencer introduced this kind of method and this approach to solving combinatorial problems is basically like kind of a four-step process. You introduce randomness, you identify the desired properties that you want or you want to avoid, you then calculate some probability, either less than 1 or greater than 0, and then you're basically done. They kind of skip over that fourth step. They're basically finished. So we want to look in our framework, how can we set this up in a formal environment and make it easier for people to just kind of get started on probabilistic proofs and reduce the duplication between different probabilistic proofs. So we might start off with defining a probability space. So instead of randomness, just this intuitive notice of randomness, we actually have to formally define, going back to kind of probabilistic basics, what's the space we're working in. Step 2 is very similar and very problem specific. We can't generalize that anymore. Step 3 is our calculation step. And this is where those techniques that were around that circle I showed you before come into play. Yes, calculations are very much specific to each individual kind of theorem we're trying to prove, but the techniques involved in those calculations still have some potential for generalization. And then 4, we have to do that last step in a formal environment. We can't just skip over it. So we've got to do this basically what I call the obtain step. So it's an existence proof to finish off our formalization. So let's look at the first step to start off with. Here we introduce a probability space, and this is how that kind of first proof when I was setting up a probability space looked like. We defined a probability measure. We then showed that this measure was actually a valid probability space. And then we set up a number of kind of useful facts, and this was all done within the context of a kind of single proof statement. And a lot of these facts in particular, they're very basic, they're quite general, but if you formalize them at the start and name them in your proof in Isabelle, the automation down the track becomes so much nicer. So we definitely want to do this, even though it's quite basic to set up. But obviously a lot of these are quite, repeated. So anytime, in this case, it's a probability space over vertex colorings, anytime we want to do a proof on this kind of similar probability space, we've got to do the same setup at the start of the proof, which is an obvious amount of generalization. So my solution uses locales, which is Isabelle's module system, for those unfamiliar. Locales are a fairly simple concept, but quite powerful in what they can do. Effectively, you have a number of parameters defined using the fixer statement and a number of assumptions. And then within a locale context, you can work with those assumptions as if they were facts and those parameters very naturally. And there's a lot of kind of different things you can do with locales. And there's some more detail in the paper if you're interested in that. So particularly what's quite powerful about locales is their inheritance. So you have both direct and indirect inheritance that you can set up, and you can also interpret an instance of a locale structure, so you can use that naturally in a proof. So my initial approach actually was quite inspired by something Nishinsky did in the first formalization I could find using the probabilistic method, where we take a lot of this setup and we put it inside a locale, calling the vertex color space locale. Now this builds on a very basic hypergraph kind of structure. It's single parameter, added on top of that is the number of colors which you're modeling, and then those definitions, they become local definitions inside your locale context. That interpret statement for a probability space, that becomes proving a sublocale relationship, so establishing inheritance. So within your vertex color space, you get all of the properties of a probability space. And all of those local lemmas now just become lemmas within your locale context again, so you don't need to repeat them each time you interpret it. So now we can replace all of that work there by a single interpret kind of line. So we can generalize this further, because even in that I was thinking, well, I had to do a lot of exactly the same steps, but on a graph for my Bell-Examer-Rady-Gowers proof. So can I generalize this further? And of course we can. This is again using locales and their inheritance pattern. And And we start off with some very general locales, basically, on a basic instance system. So any kind of set system, which is what a lot of combinatorial structures build off, where you have some kind of vertices or points and then collections of those objects. And at the top level, we kind of introduce randomness or a probability space as some kind of property on vertices. So this could be anything from selecting at random a subset of vertices, say in our graph, or it could be something more specific, like assigning a colouring. So we can do a lot of kind of different ways of introducing randomness on the points or vertices of our graph or instance system. And then using locales, they have this really powerful rewrites command within your sublocale definition. And this was actually a really important part of setting up this hierarchy, because we wanted to generalize, but we didn't have to then add in more simplification proof later on to retain natural notation. So by putting this rewrites command here, basically assigning omega to being the set of colourings in the inheritance declaration, it means we don't need to do any kind of simplification or rewriting proofs as we use that. We can use the colouring notation very naturally, even though it's inheriting all of those lemmas from more general locales. Cool. So that was a big part of the work in terms of the general step. Step 3 starts to look at the calculations. So here we have basically some simple ones to start us off with. And the two simple ones that they look at in the textbook is the union bound and the complete independent bound. These are both fairly simple probability lemmas. The first one was really just lifting it from the measure theory libraries, so it was easier to apply in a discrete kind of probability space setting. The second one, I couldn't find an equivalence lemma anywhere in the measure theory libraries, so do a bit more work, but it was still fairly straightforward to do. And I formalised a number of versions of each of these lemmas, again trying to make it as easy as possible for someone who's coming in, wanting to do proofs using the probabilistic method to make use of these calculation steps. Great, so then step 4 is that obtain step. Again, these are basically just existence proofs. So there's one for being less than 1, one for being greater than 0, basically to help us make that last step in our formal proof. Wasn't that difficult to formalise, but necessary in a formal environment. And even we did a few lemmas which combined both those steps 3 and 4 for the really basic calculation steps. Great, so now I'm going to jump back to step 3 because I want to introduce a more advanced technique as well to this framework that I was developing. And specifically, that was the Lovász local lemma. And if you look at the formal libraries that are kind of attached to this paper, this is easily where the most formalisation work happened. That said, I'm going to skim over a lot of that detail in this talk just to save us some of the time, but kind of aiming to give you an idea of what was involved. So the Lovász local lemma basically gives us a bit more of a relaxed condition from the complete independence bound. So rather than requiring that all events are independent, we simply require that one event is mutually independent of some other set of events, and for that other set of events, Ni, which is often modelled by a dependency digraph, so something that models the dependencies between probabilistic events, we have this slightly more complicated inequality that has to hold. And if that holds in all cases, we basically get the same conclusion. So it's a weaker condition, it's a really powerful lemma in probability with a lot of applications, particularly in this kind of probabilistic method for combinatorial space. So we formalise this. This is what the formalisation looked like. It follows fairly straightforward from the textbook kind of statement of the theorem. A few little things we had to do differently, like it introduces these real coefficients xi, so we just did a function that kind of maps those for each individual event. And we obviously had to formalise what dependency graphs were as well. So that we did building on a pre-existing digraph formalisation in Isabelle. So what did the formalisation of this lemma actually involve? So I'll save you from any more Isabelle syntax and kind of give you an idea, I guess, of the main kind of formalisation challenges generally. So how the proof works on paper is that very much most of the proof is in this helper lemma. They do a helper lemma and then they apply to finish the general Lovász local lemma. What's interesting is that the proof of the helper lemma was basically an induction proof. There was also an induction proof in that general Lovász local lemma proof, which was quite hidden. It wasn't specifically stated in any of the textbooks that I found on the subject, I actually only found one set of course notes that even touched on the fact you needed to use induction here. And when I kind of asked some people about it, they're like, oh yeah, well obviously that's basically what you're doing, but we don't really worry about the detail of it. So that was an interesting kind of typical formalisation challenge that we had to come across. This also exposed some issues with Isabelle's probability library, which I'm going to touch on a bit more later. A lot of basic setup work in terms of actually contributing to the probability libraries, so establishing things like conditional probability, and defining a lot of related work in that space. And then keeping in line with the fact that I want this to be easy to apply to different contexts, I formalised several different versions and corollaries of this lemma as a result of that, including both using the dependency graph form and using a more mutual event kind of set format. Cool, so now let's have a look at some applications. So, the first application is going back to this very basic proof on hypergraphs that I showed you at the very start. So hopefully now our framework should be able to tackle that pretty easily, and we can get rid of those really long proofs that I showed you at the start. And it does in fact work really nicely. You can see really clearly each of the 4 steps of the formalisation of that basic method in the formalisation. Setting up the probability space is now that one line. Again, defining events, fairly straightforward. Calculations are the most involved, they're problem specific, but we still benefit from some of the techniques that we set up. Specifically, that last step kind of combines the union bound with the obtain step, and also the idea of using locales to set up the probability spaces very much encourages modularity. So for things like when it says calculate this probability, instead of calculating that probability for this proof, we calculate that probability in a much more natural environment within our vertex color space locale, which is set up to reason on probability spaces, and then it's a one-line proof in here. So it means that your proofs of actual applications are much simpler and cleaner and more closely reflecting what you might see on paper rather than being cluttered with a lot of extra information. All right, so now let's look at a more advanced bound for an application using the Lovász local lemma. Again, you might think, oh, well, on paper, this is actually shorter. Isn't that great? We're going to have so much fun formalising this. It wasn't smaller in an actual environment. But still, we can see that we retain the structure of the formal proof kind of structure and that general framework that we set up. We don't need to do anything extra to set up the probability space. That's our simple one line again, exactly the same as before. There's a little bit of extra setup to actually use the Lovász local lemma, which is the next few lines in the definition, but defining the event, similarly simple, and then most of the work again goes into that calculation step. What's eminently nice is that when we do that calculation step, we do an intro Lovász local lemma kind of thing, which sets up 3 clear proof goals, which are basically your assumptions to prove a property using the Lovász local lemma. So we immediately give structure to our calculation-based proof because we've formalised this technique separately. There was again some interesting crossover here. In the proof on paper, they only proved 2 of the 3 assumptions that you need to use the Lovász local lemma. So there was an extra assumption they just completely forgot about. Thankfully, that was a fairly automated proof, thanks to Sledgehammer. There was a calculate the probability step again, probability inequality. Thanks to our modularity, that was actually basically already proved in our vertex color space locale from the previous thing. So that was similarly simple. Then there was this, moreover, each event is clearly mutually independent from the sets, from all the other events where you've got that intersection property. It's not clearly mutually independent. And it was actually funny going through textbooks. I found one textbook which had a sketch of the proof for this part of what they actually rely on, something called the mutual independence principle, which was stated in several places, but no one ever explained what it was. So this was actually a lot of work, and I think it was actually one of the interesting contributions of this work as a result is we had to do the proof of this principle, which is really important to be able to use the Lovász local lemma in other contexts as well. And so that's one of the things that we were able to contribute through the formal environment that was often just skipped over on paper. Cool, so I want to finish off with a few key insights. So the main one is intuition. And intuition, as I said, in probability, it happens in a number of different ways, which is quite interesting and a little different to what I've seen elsewhere. The first one being introduce intuition and randomness. And I actually had a really interesting conversation with Timothy Gowers when I started this work. And he was like, yeah, well, yeah, it's very flexible how we're using probability as in combinatorics on paper. And it's a real challenge for formalization work, actually. How do we go about setting this up? Because you would never define a probability space formally on paper to do these kind of proofs. And I think that's actually one of the barriers I've seen in even a few other papers, including my own, to be honest, where someone said, we're avoiding the probabilistic approach because of the setup involved in kind of doing it. And so that's very much one thing this framework aims to help solve. The next one is obviously the end of that step. So we kind of tail and we do both kind of parts of it. So we have to obtain that exemplar structure. It's a simple proof, but it's a necessary step in a formal environment. And again, now this framework aims to mean that's all set up, so that's quite easy to do, hopefully. And then there are many calculation-specific examples. So I hinted at this when I talked about the mutual independence principle. Independence was a real pain to formalize. And it was actually quite interesting thinking about why this is. When you think about independent events, as we maybe are taught in high school or something like that, you look at things and you might go, well, clearly these events are physically independent. They don't affect each other. So therefore, because they're independent, we can use the multiplication rule. And even you see this as well in a lot of more advanced proofs. People go, oh, clearly these two events don't affect each other, so we can use the multiplication rule. And then you look up, well, how do we define independent events formally? You define independent events if they satisfy the multiplication law. So we have a little bit of a circular reasoning kind of problem going on here, which I was really quite fascinated to come across, to be honest, because it's just so routinely used in these kind of fairly advanced combinatorics proofs that they can rely on this, but still how we're defining independence to start off with relies on this formula. And so that meant, as a result, a lot of the calculations I had to do in a formal environment, I had to go back to counting techniques. I had to go back and infer mutual independence by a more kind of complex or kind of foundational way from how we define the probability space. And that was a lot of the extra work involved in formalizing these proofs. So it's a really interesting example, I think, of mathematical intuition at play. Next one, an Isabelle probability library issue. And I will admit, this is the first time in 4 years that I got a bit frustrated with Isabelle's foundations. But there was basically this issue where your probability space in Isabelle and how the probability library is defined is not equivalent to the universal set. For example, in our coloring kind of context, we define vertex colorings as basically functions from each vertex to a color. And that clearly is not equal to all functions of the type -a to a natural number, right? So we definitely have this disparity in what happens here. Whereas on paper, we see mathematicians routinely switch between using the probability space and using the universal set in their notation. And again, from what I can see, this doesn't appear to be an issue in Coqueline when I had a quick look into it. So I do think there's probably solutions, and I do think that we could go and have a look at the probability library as it is. Not something I had time for personally, but I think that's definitely an interesting problem to put out there, because it meant a lot of proofs. It really wasn't a problem until you came across something like this. You take the big intersection over an empty set, and that's the universal set, which was often the base case for those inductive proofs I talked about, and that meant that I now had to go with the base case of a set of size 1, which was a lot more complicated from a calculation perspective. So there were some less desirable kind of things that I had to do. Still possible to do a proof. Definitely doesn't stop us from doing any proofs, but it is a complication. And the last thing I want to talk about is generality. And this is both kind of something I found and also something that I think this work really tries to contribute to. There were several cases that I had to build on the probability libraries, and there were things that had been formalized, but for very specific use cases. And this is common for anyone who's done formalization work, especially in mathematics, in older systems, where things just aren't easy to reuse in different contexts. So it's really important for us to look at that as formalization, as we're doing these mathematical formalizations, particularly as these libraries continue to grow at this really quick speed. And I think we're seeing more of this come into play now. So this work, I think, has hopefully successfully showed how we can actually establish some frameworks and some general techniques to help us. It's not going to be able to do everything, but definitely can help us and reduce the barriers to entry for doing certain kinds of proofs in a formal environment. That said, I do think there's a balance between like the practicality of it and the generality, right? And being able to actually use it. So when I say it's an interesting balance for general techniques, because I did lift lemmas from the measure theory library. And I did that because it was easier for the automation and it was easier to apply those in a discrete context. Those are slightly less general lemmas. So we have this kind of mix of things generalized at the very base level, kind of mathematically from a foundations perspective, and then also general techniques in certain spaces, right, to make doing different kind of proofs easier. So yeah, to finish off, the key contributions of this work, very much looking at a lot of expansions to the libraries for probability in Isabelle, this general framework, and the proof of the Lovász local lemma, along with this little bonus of the mutual independence principle and a few applications that we looked at. I do really want to emphasize that obviously the applications we looked at were hypergraph colorings, and I have already seen some success in going back to, say, the proof I did last year on graphs, which was a completely different context, and it both improved the automation of a number of proofs and got rid of some of the extra setup that we had previously. So this is really much, those are very much sample applications, and I think there's a lot of potential for further applications using a very similar, and using this framework. And I guess, lessons, generalization is both possible and important, and formalisation can give us insights not just from a formalisation perspective, but also, I think, into some kind of age-old ways that mathematicians think and approach problems. All of this work's available online, and I'm very open to any questions. Thank you.
Thank you. Are there any questions?
Hi, thanks for the talk. I was wondering, you said that you heavily rely upon locales because of the automation that you receive out of it. Is there any missing features of locales that you would say, well, if locales would support also this, then I would be even happier, less manual work would be required?
Yeah, I think that's a really good question. There's definitely, I think, some more potential for different proof tactics. So in terms of setting up at the moment, we've kind of got intro locales and unfold locales being the two main proof tactics to set things up. I find I often have to do kind of an intermediate step sometimes with those. And there's also, so I think we could potentially write a few more tactics for how we're unfolding different levels of that locale infrastructure to make it a bit easier. And then also a few notation things that mean it's really quite bulky to type up, and I think that we could, to some extent, automate, or at least not automate it, but make it easier to deal with having a lot of parameters, for example, which add up over time. To be able to bundle things in some capacity would be quite handy, while still retaining the benefits that locales offer us by having those as individual parameters and not having to deal with record types, for example. So those would be the two immediate ones that come to mind, though I think there's probably more as well.
Okay, thanks.
Here we have another question.
Yes, thanks a lot for your talk, very interesting. I was wondering about you're saying about mutual independence, and there's some confusion about that in the theory that you formalized.
Yes.
Does it in any way relate to the concept of k-wise independence? So like sometimes you want to limit it to like a finite set of things that are independent between each other? Yeah,
so it's probably, I think, potentially something similar. So when I talk about mutual independence, I mean, you can use this vocabulary in a lot of different ways. Some people talk about just a set of events all being mutually independent of each other. In this context, and in the textbook I was using, that refers to an event being mutually independent of a set of events. So that set of events itself doesn't all need to be mutually independent from each other. So I don't know if that's similar to what you're talking about.
Right, so k-wise is just when you have a finite subset of events that need, of size at most k, that needs to be mutually independent.
So it's not quite the same, because it's one event being mutually independent of a set of events. So you kind of take this, basically if you look at, say, the definition of independence where you'd unfold an all, you'd have to kind of each individual one multiplied by each other is the same as the intersection over all of them.
Because I can see that sometimes they're used interchangeably.
It's a classic language example in mathematics, right? Where we use different notation and definitions to refer to slightly different things.
And then you're just making the assumption that it's more or less the same, but it's not really.
Yeah, exactly. So it's one of the things I think formalization has the potential to help, because obviously we can only define things using something each way, and it's quite specific. On the other hand, it's a challenge for us because people might define two different definitions, name something different that are the same thing. So it's an interesting problem for sure.
Very interesting. Thanks a lot.
Thank you.
Okay, I have a quick question, but maybe René can set up. Okay, there is a question from the audience, so take this one. Please come to the microphone, and you should set up René already.
You mentioned the difficulty of setting up probability spaces because in traditional mathematics we typically don't state probability space, but instead just create new variables, random variables along the way, and not all of them at the same time, sometimes later, sometimes with probabilities depending on previous results of realization of probability. Do you think this approach of not doing formal probability space, even though we actually should in mathematics, is actually dangerous or prone? If not, do you think we are anywhere close in proof assistance to being able to define variable in that kind of way, a bit like in a programming language, rather than having to state all of our variables and state at the beginning?
Yeah, that's a really good question. I think as with any intuitive mathematical thing, there's always potential for it to go wrong. So especially as you start dealing with a lot more random variables and things like that, I do think that if we were just to rely on that way of doing things, that there's definitely potential in there for something to get disconnected. I can't name an example off the top of my head, but I think that'd be something quite interesting to go and look into. I do think it'd be nice if we could somehow start to mirror some of the kind of ideas in that language of how we're introducing randomness naturally on paper in a formal environment. But basically, if we could set up some tools to do it in a way where it still has all that probability space set up, but we're just maybe able to automate some of it to some extent. And in some ways, like as we've seen here, there's a lot of repeated steps and things that we're doing each time. So I can definitely see potential to potentially automate some of this process. We're not there yet, but that's, I think, something that'd be quite nice to look into if we could find some kind of middle point between this natural way people introduce it on paper, but still having the formal backing. So, yeah.
Thanks a lot. Great talk.
Yeah, thanks a lot for the great talk indeed.
Thanks very much.